I'm going to need your help thinking today because I can't think in weather like this. It's impossible. But so a lot of Colombia is very hot, but actually Bogota, where I'm from, is up in the mountains. It's like 8,000 feet high, and so it's just perfect San Francisco weather year-round. It's like 60 degrees year-round. So this is too much. So we were talking about, I was teaching you a little bit about linear programming so I can prove to you a theorem about matroid polytopes. So let me remind you what we said last time. We talked about linear programming. So a linear program is a problem like this. Maximize a linear function, which we write as C transpose X. So remember, this is just a dot product of C and X over some polytope in Rn, defined by the inequalities ax less than or equal to b, x bigger than or equal to 0. We said that you have a dual linear program, which lives in Rm now. This one is in Rn. This one is in Rm. The dual linear program asks you to minimize b transpose y over a different polytope, a transpose y bigger than or equal to c, y bigger than or equal to 0. So somehow b and c kind of reverse their roles here and here. And here you're maximizing, here you're minimizing, and here you have less than or equal, here you have bigger than or equal. We saw an example where this polytope looked like this, something like this. And we wanted to maximize a linear function that was headed in pointing to this direction. And then the dual program looks something like this, where now the polyhedron was something like this, and we were supposed to minimize in this direction. So here we're maximizing in this direction, here we're minimizing in this direction. And so this was the optimal point. I asked you guys to check that for your, as an exercise. This was the maximum point for this linear program. So this is the highest point according to this linear functional in the polytope. And the lowest point in this direction is this one over these areas, which are called the feasible regions. These are the feasible x, and these are the feasible y. Okay? And the story that I told you about linear programming duality is that solving these two questions they're kind of equivalent problems. And in particular, I talked about weak linear programming duality, which said that if you take any feasible x and y, then the value of the linear function at x is less than or equal to the value of the linear function at y. And actually, if you manage to find u and v that give you the same value, so the linear function at u equals the linear function at v, then that is the optimal value, and you have solved your linear programming question. Okay? And then I told you about a strong linear programming duality, which said that if you have an optimal solution here, then you have an optimal solution here, and the value is the same. Remember, when I talk about optimal solution, I talk about the point where the solution takes place. When I talk about the optimal value, I mean the value of the function at this point. So that's where we were. And the reason for doing this was that I was going to prove a theorem for you, basically saying that, giving you the inequality description for the matroid polytope. So if M is a matroid, I said that the matroid polytope was given by the system of inequalities. Let's say that it's on E. So first of all, any variable has to be positive. Second of all, the summation of all the xi's has to be equal to the rank of the matroid. And third of all, if now you don't add up over all the variables, but only over some of the variables, let's say a subset A of the variables, then that is equal that is at most the rank of A.
So not last time, but before, when you defined the matroid polytope, you said that those all are 0, 0, 1. all their vertices
Right.
are 0 to 1.
Maybe I should remind you what the definition of the matrix polytope is. It's the convex hull of the vertex of each basis. Where the vertex of a basis is a 0, 1 vector that has ones wherever the basis is. So for example, this is b sub b when b is equal to 1, 2, 3, 4, 5, 6, 7. 4, 5, 7. So this is the definition of the matrix polytope. And I'm claiming that, and I said that these were all the vertices. I proved that last time. And I'm going to show that these are the inequalities that describe that same polytope. Okay? So, proof. What I said last time was that I was going to call this guy Q sub m, and then I was going to show that these two are equal. So let me call this guy Q sub m. And so what I want to.
So your theorem is.
So goal is that P sub m is equal to Q sub m, and so let me just say this is a definition. And what the theorem is that they're equal. Okay. And last time we showed one inclusion, so we showed that any of these vertices, any vector of this form, satisfies these three inequalities. So each point v sub b is inside Q sub m, and therefore, because they're convex sets, because Q sub m is convex, the convex hull of P sub m, the convex hull of the v sub b's, which is P sub m, is inside Q sub m. So I proved that last time. And this time, I'm going to prove the opposite inclusion. The Q sub m is contained in P sub m.
It looks like with this definition or set of hyperplanes here that it's actually living when it's living inside a hyperplane, so we know that ground will be voltage.
Exactly. So, for example, we know immediately that this polytope is not full dimensional. It doesn't have e dimensions because we have an equality. And actually, it might be that we have more. And we'll see that sometimes there's some hidden equalities here because we have an inequality that says, x plus y is less than 3, and another one that says x plus y is bigger than 3, which gives you an equality. We'll see about that. But immediately we know that this is not a full dimensional polytope. How am I going to show that Q sub m is contained in P sub m? What I'm going to show is this. I'm going to show that take any vertex, let's call it P of, actually let's call it Q so that it makes sense, Q of Q sub m. And I'm going to show that actually that vertex Q is one of the vertices of P sub m. We'll show that actually Q is a vertex of P sub m. If I show that, then that will show that any vertex of Q sub m is inside P sub m, and therefore all of Q sub m is inside P sub m. So this will imply Q is inside P sub m, and therefore by convexity, all the vertices, since each vertex is inside P sub m and P sub m is convex, that means that all of Q sub m will be inside P sub m. Okay? So the picture is like this. Let's say that we have Q sub m, and then P sub m, as far as we know, lives inside it. And now let me consider some vertex of Q sub m. Okay? Let's say that it's this one. And again, how do you describe a vertex of Q sub m? Well, you say this vertex Q is the point that maximizes some linear function. So let's say that you have a linear functional like this. And let me call it, to be consistent, I'll call it, what did I call it? W. Okay. So let W, where are we living here? This is RE, right? So let W be some direction in RE such that W transpose Q is maximized at, such that W transpose X, or X in the polytope, is maximized at Q. So what I'm saying is just that pick some direction so that Q is the farthest point away in that direction. Okay? And then what I'm going to try to show is that actually Q is equal to this vertex that maximizes W inside P sub n. That's what I'm going to try to show. Okay. So let me call this guy U. So let U be inside let U be the vertex maximizing W transpose X in P sub n. So I will show that actually Q is equal to W. Q is equal to U, rather, which will be what I want to show. I want to show that Q is a vertex of P sub n. Okay. Now, the point is that I want to use linear programming, right? So there should be a linear program here. And you see that actually we have exactly a linear program because what we're doing is maximizing W transpose X over a polytope. So what's my linear program? We want to maximize W transpose X in the polytope Q sub m. And Q sub m is given exactly in this form. Some inequalities less than or equal to b, and all the variables bigger than or equal to 0. You see here you have a bunch of inequalities. Some linear functions of the xi are less than or equal to the rank, and the xi's are positive. So what's my linear program here? It says this. Let me show you what the linear system looks like. So the inequalities are going to look like this. I have an inequality for each set, right? And so, for example, x1 plus x2 is less than or equal to the rank of 1, 2. Or x2 plus x3 is less than or equal to the rank of 2, 3. So I'm going to encode those like this. So, for example, the dot product of 1, 0, 0 and x1, x2, x3 is x1, and that's supposed to be less than or equal to the rank of 1. This times x1, x2, x3 is x2, less than or equal to the rank of 2, and so on. For example, 1, 1, 0 times x1, x2, x3 is x1 plus x2. That should be less than the rank of 1, 2. So let me just write all of them. So 1, 0, 1, 0, 1, 1, 1, 1, 1. rank of 1, 3, rank of 2, 3, rank of 1, 2, 3. So far I'm just writing these inequalities, right? And now I actually need another inequality, because this says that the sum of the variables is equal to the rank. In other words, x1 plus x2 plus x3 is equal to the rank of 1, 2, 3. I already have x1, x2, x3 is less than or equal. So now let me just write the negative inequality of that. Minus 1, minus 1, minus 1. And then minus rank of 1, 2, 3. And that's going to guarantee an equality, because I put an inequality and its reverse inequality. Okay. So these are all this list of inequalities, and then xi bigger than or equal to 0.
Wait, I just need the minus on one. 1, 1, 1, less than.
I'm sorry?
Minus.
So this is minus x1, minus x2, minus x3, less than or equal to minus the rank of 1, 2, 3. So this is my linear program. And by definition, Q is the solution to this linear program. And it's the only solution because I'm assuming that Q is the one vertex. I mean, I picked W so that it's maximized exactly at the vertex Q. So by assumption, Q is the only solution to this linear program. Okay.
It's because it's a vertex.
Because I chose Q to be a vertex, and then I chose my direction to maximize exactly at that vertex. Okay. So that is my linear program. Okay. And so I'm going to write now the dual linear program and see what that looks like. So dual linear program. Well, let's figure out what each thing is here. So in the notation over there, I'm maximizing C transpose X, so therefore this is the guy that I'm thinking of as C. This is the matrix that I'm thinking of as A. And this is the vector that I'm thinking of as B. And so now I need to minimize B. No, sorry. B is now this rank. What's a good name for this? Well, let's just call it B. I called it B over there. So minimize B transpose Y in the polytope. Now I'm supposed to take A transpose Y bigger than C. So I need to flip this matrix around. So now it looks like this. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, minus 1, minus 1, minus 1. This is A transpose. Then I need to multiply it by some vector Y, which is now, this is of size E, and this is of size 2 to the E. And so now I need some long vector of length 2 to the E, which actually, let me give it some names. So I'm going to call it I have an entry of the vector per column of this guy. And so a natural way of labeling this is to call the first one y of 1, the second one y of 2, the third one y of 3, the fourth one y of 1, 2, y of 1, 3, y of 2, 3, y of 1, 2, 3, and then some extra variable, which maybe I'll just call y. Okay. So this is just kind of a typical vector that you can multiply by this matrix. And this is supposed to be bigger than or equal to W, which is W. Now, what does this B transpose Y look like? Well, I'm not supposed to write here. Huh? B transpose Y. So B transpose is the transpose of this column vector, which basically just keeps track of the ranks of all the sets in the matroid. Okay. So rank of 1, rank of 2, so on. And then I multiply that times y of 1, y of 2, so on. Okay. And well, just to get the sizes right, let me call this W, W1, W2, W3. Just to make it clear that it's the same size. Okay. So here's my linear program. Here's my dual linear program. Now, what is it that I'm going to try to pull off now? Well, my goal is to show that Q and U are the same point. Okay? U is the point that maximizes the linear function W. Okay? Now, when I talk about a vertex of P sub m, I mean a basis. Right? So here what I'm looking for is a basis that maximizes over a function W. And that should sound familiar to you. What we're looking for here is really, you should be thinking of W as a weight vector, and you are looking for the basis that maximizes that weight vector, which we know how to do very well. And so basically what I'm going to try to do is say, well, I think that U is the optimal solution. And the way that I'm going to prove that U is an optimal solution is to use weak linear programming duality, where I'm going to find U and V that satisfy C transpose U equals B transpose B. And if I find that equality, then I'm going to be done, and that's going to be optimal. And that's going to prove that the optimal solution is U. That's my plan. That sounds like an ambitious plan, but we're going to do exactly that. And the good thing about this is that we exactly know how to optimize over basis of a matroid, because you guys did that in your homework. Okay. So let's see. Go over here. Maybe I'll erase this, but keep this. Yep.
In the class last time, your bullet 1 was what you were defining as weak, and your bullet 2 was what you were saying was strong.
Uh-huh.
But it sounds like now you're saying both of these are weak, and there's some other condition that's strong.
Yeah, so there is something else called strong linear program duality, which is what I said, that if the primal linear program has an optimal solution, then so does the dual, and the value is the same. But I'm not going to use that. So I'm only going to use weak linear program duality, which is why I only mentioned this one. There is a strong one that I'm not going to use today.
Wait, that's like a converse of the second condition you have there or something?
Yeah. 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 It's not exactly a converse. It's just a stronger statement. It says actually, because sometimes linear programs don't have an optimal solution.
Okay.
But it's saying if a linear program does, then so does its dual, and the value is the same.
This is just saying if you happen to have two guys that equal,
Then you're done.
optimal.
Yeah, exactly. Okay, so what is U? And remember, U you should be thinking of as the basis that maximizes a linear function. Okay. What is U? Well, it depends on W. So let's assume that W looks like this. W has a bunch of entries equal to each other, which are the biggest ones, then the next ones, then maybe like this, maybe like this.
You can always assume that the W's are all positive, right? Is that right? Or not necessarily? How do we do that?
I'll let you guys think about that. The reason that I can assume the W's are positive is this last thing, this last inequality. But actually, it doesn't even really matter, I don't think, because the point is we have a weight vector, right?
Yeah.
And now remember, how did we pick the basis that was maximal with respect to this weight vector? So we did this in several different ways, but basically the point was just, if you want a basis, what am I choosing here? I'm choosing a basis, which I'm going to write as a 0, 1 vector. And the greedy algorithm tells us basically take as many ones as take as expensive weights as you can if you want to maximize the weight of your basis. So that means A is the most expensive element of the matroid. I should take it as long as it's not a loop. If it's a loop, I can't take it because it's not independent. But I should take it if I can, if it's independent. Then how about B? Well, I should take it if AB is independent. Otherwise, I can't. How about C? I should take it if I can. The point is basically I should just take as many guys here as I can. And how many can I take? Well, I have a set A, B, C. And so the size of the largest independent set there is rank of A, B, C. That is the largest number of elements of these guys that I can choose, so that I'm choosing an independent set here. Okay? In other words, and you guys did this. What I'm doing is just choosing a basis for the restriction matroid on A, B, and C. Okay? Then I go to D, E, and F, which are the next most expensive things, and I choose as many as I can. Okay? How many can I choose? Well, basically, I can choose at most rank of A, B, C, D, E, F guys here. And so I just put as many ones here as I can, and the number of ones that I can put is exactly rank of A, B, C, D, F minus rank of A, B, C. And I continue doing this, so maybe I take as many of these as I can, maybe. And the number is given by rank of A, B, C, D, E, F, G, H. And then I take as many ones as I can here. And the number of them is rank of A, B, C, D, E, F, G, H, I, J, K. By the rank. So, for example, in this example, I assumed that the rank of ABC is 2, meaning that I can take 2 of these guys. Then I assumed that the rank of ABCDF is 3. So I assume that I can take these 3 guys, but no more. Then I assume that this rank is 5. So I can take up to 5 guys, but no more. And I assume that the rank of the total thing is 7, which meant I can take 1, 2, 3, 4, 5, 6, 7. Okay. And so just in this example, I made these numbers up, but in general, you're given a matroid. And by the matroid, you know what these numbers are. And that is the number of elements that you can take from here, from here, from here, from here, etc. Okay? And actually, this might be a little bit misleading because it's not necessarily true that you can pick A and B. You just know that this is a rank 2 matroid, and therefore it has some basis. And so you just pick a basis. So maybe A and B were dependent, but A and C are independent, so you pick those. And maybe this looks more familiar if I write it as, what you're doing is taking a basis of the matroid restricted to ABC, direct sum, the matroid restricted to A, B, C, D, E, F, contract the matroid of ABC, so on. This is that homework question where you guys did exactly this.
So
And so I'm basically, what I'm saying is that we know that this guy is a basis of maximum W weight.
We also know.
But one thing I should point out to you is that actually the weight of this basis is WA plus WC plus WD plus WG plus WH and so on. It's exactly the dot product of these two guys. So that's why what I'm doing here is exactly maximizing weights over basis of the matrix. Okay. So this is the U that I'm talking about there. Okay. This is that purple U that I have in my picture, the direction that maximizes p sub m. Okay.
So we know that guy's unique, right?
And actually, it might not be unique. So it might look like this because,
Oh.
I mean, W was some direction, and it could be that Q is the only vertex that maximizes W, but it could be that in that direction, you have two guys here, U and V. I shouldn't call it V because I want to use V for something else. So U and U prime
You mean in the small in
in P sub M.
P sub m, you could be that you get a whole edge or whatever.
You could get anything here.
But
You
then
could get a lot of things, but I'm just choosing one of them.
Okay.
Okay? And so that's why I said we know that this is a basis
Yeah.
of maximum W weight. I don't know that it's the only one, and it might not be, but it's the basis of maximum weight. So that's the U that I'm going to try to plug into the theorem here. And therefore, what I want to do now is compute C transpose U. But we have to remember what C was. So C was the weight vector, and U was this guy. So really, when I talk about C transpose U, I'm really talking about W transpose U, which is exactly the weight of this basis. Exactly the weight of this basis, which I'm going to write in this way. I think the most difficult thing about this proof is to find a good notation for it. But what I'm going to do is basically, let me call these weights W of 1. Okay? The heaviest weight is W of 1, and it's repeated. The next heaviest weight is W of 2. The next heaviest weight is W of 3. The next is W of 4. Okay? And let me call this set ABC S sub 1. Let me call ABCDF S sub 2. This one S sub 3. And this one S sub 4. Okay? And so, what is the weight of this basis? Well, it is. How many elements of weight W1 did I choose? 2, because that's the rank of S1. Plus, how many elements of weight 2 did I choose? I chose 1, and the reason is that 1 is 3 minus 2. The rank of S2 minus the rank of S1. Then the number of elements of weight 3 that I choose is the rank of S3 minus the rank of S2, and so on. Okay? Until the last weight. So this is WT of U. Okay? Well, I want to take this expression and write it a little bit differently. Because here I have a term associated to W of 1, a term associated to W of 2, to W of 3, and so on. But let me now reorganize and instead say, let me first group the guys that have rank of S1, then the guys that have rank of S2, and so on. So this thing is equal to rank of S1 times, where is rank of S1? Well, you have W1 minus W2. Plus rank of S2 times W of 2. See it? Rank of S2, W of 2 minus W of 3. Plus dot, dot, dot. Maybe I should just put a last term here. So if the last term here was W of K times rank of Sk minus plus 1 minus rank of Sk, then the last guy that you're going to have here is, this is not the last, well, this is not the last one. This is the next to last one.
Yeah, that's
K
K
minus.
plus 1.
Did I do that wrong?
Wait, W of K.
Oh, no, sorry, this
equals
is,
R of S sub K minus R of S sub K.
right, R of S sub K minus R of S sub K minus 1. And so, let me put the last two terms here. R of S sub K minus 1 appears in W of S sub K minus 1 minus W of S sub K. And then the last guy just appears as W of K. And actually, this is W of K minus 1 minus W of K. So I wrote W transpose U in this way. Okay. But you see, that's interesting because actually this guy looks exactly like a dot product of a bunch of ranks with a bunch of other things. And that's exactly what we're looking for here. A dot product of a bunch of ranks times a bunch of things. So this is the dot product of this is the dot product of the vector of ranks, which I called B, times some guy here, which I'm going to call V. And what is V? Well, this is the dot product. So the idea is that basically this is V of S1, this is V of S2, this is V of Sk minus 1, and so on. So V of S1 is W of 1 minus W of 2. V of S2 is W of 2 minus W of 3, and so on until V of Sk is W of K. Does that define B? Again, remember that the length of this guy,
Wait, why are you calling that B now?
just because it's this V that I want to get. So I'm just define V to be
Why is this guy called B? This is not necessarily.
B. Well, so what is B? B is
This B over here.
this B that has the rank of
Yeah.
each element, each subset. So B is
Okay, yeah.
has length 2 to the E.
So you need some zeros
Okay.
in your V, or something like that, right?
Or you need some zeros in this.
So
Not in the V.
so that's precisely the point that I was trying to make, that this guy has length 2 to the E.
Yeah.
This guy has length 2 to the E. And I've only defined, I'm supposed to define V for any subset.
Yeah.
But I've only defined it for these subsets, S1 up to Sk. I need to define it for the other guys. b of anything else, what should I define it to be? 0. And the reason is that basically by doing that, I'm going to accomplish that v just ignores everything that happens at b except at these ranks. Okay. So this I define as v. And so what did I show? I showed that W transpose U equals B transpose V. Right? This is W transpose U, which is equal to B transpose V. Okay? I want to conclude using weak linear programming duality that this implies U and V are optimal. So let's see if I have all the conditions that I need. Weak linear programming duality. Second item says, if I have the equality, and I do have the equality, for feasible U and V, then U, V are optimal. So we're all done as soon as we can get this adjective taken care of. As soon as we can show that these guys are feasible.
We know U is feasible, right?
Now, is U feasible? U is feasible, and the reason U is feasible is that we chose it to be a basis of P sub m. So it's inside Q sub m. And feasible means you are inside Q sub m. So U is feasible. U
That means it's inside P sub m.
is inside P sub m, and therefore it's inside Q sub m.
But it's feasible for the P sub m problem. Right? We're maximizing over those two different guys.
I wish I hadn't erased this, but the
You wanted to maximize it in the polytope Q sub m.
the primal program said maximize. What letters did I choose? W transpose X over the polytope AX less than B, X bigger than 0, which was the polytope Q sub m. And so for X to be feasible means X is inside this polytope, which is Q sub m. And the way of showing that is that U is inside U is a vertex of P sub m, and last time I showed P sub m is inside Q sub m. That's why I know that U is feasible. And so my last step is to show that V is feasible.
So that means that
Where V is defined to be this thing. What does it mean for V to be feasible? It means that it is inside the polytope defined by the dual linear program. In other words, it means that V satisfies these inequalities. And that's not something obvious, and we're going to have to do it. Okay? But that's fine, we can handle it. What do these inequalities say? These inequalities say, for example, what does the first one say? y1 plus 0, 0, y12 plus y13 plus y123 minus y bigger than or equal to w1. The second one says, and so what are the guys that appear here? They are y of all the sets containing 1. In other words, summation of y of a set containing 1 minus y bigger than or equal to w sub 1.
W sub 1.
So let me just say it again. I'm looking at the dot product of the first. I'm looking at the product of the first row and the column. So what are the entries that are non-zero? Well, y1 plus y12 plus y13 plus y123. In the first row, you have a 1 exactly when the guy contains a 1. And so the terms that appear in the sum are exactly the sets that contain 1. And the second one says the guys that contain 2 minus y bigger than w2. And the third one says the guys that contain 3 minus y is bigger than W3. Okay. And so these are basically the kinds of inequalities that I have to check for a V like this one. Okay. And so let's check those inequalities. Now, the first thing, well, let me go over here and do it. So what do I need? I need that for all I, the summation for each element, the summation of V of S over all S's containing I minus V is larger than or equal to W of W sub I. Okay. Now the first thing I'll point out to you is that actually this V is 0. Because these are the V of SI's, and I defined the other coordinates to be 0. In particular, the last coordinate ends up being a 0. But it doesn't appear there.
Unless that would be.
It never appears as V as a set. V of a set. So it always gets a 0 according to this construction.
Oh, the minus.
Because that's the one with the minus inequality. Okay? Now, how did I define these S of i's? Well, and I erased something that maybe I shouldn't have erased, but S1 was a set like this, then S2 was the bigger set, then S3 was the bigger set, and so on. And so whatever is in S1 is in S2, is in S3, and so on. Now, these are all the elements of the ground set, E. And so I appears somewhere in between. And what are the sets containing I? Well, they start at S2 and they continue on for all the remaining ones. I, and so on. Okay. So in other words, this summation looks like basically V of S of something plus V of the next thing plus V of the next thing until the very last V, which is S sub k. Okay. But now what is V of SA? Well, V of S anything is W of anything minus W of anything plus 1. So V of SA is W of A minus W of A plus 1. Plus V of SA plus 1 is W of A plus 1 minus W of A plus 2. So on until the last one, V of SK is W of K. This is supposed to be greater than or equal to W sub I. And you see this argument was meant to be because everything cancels. This guy cancels this one. This guy cancels this one, and everything cancels except for the first one. So what you have to check is whether W of A is bigger than or equal to W of I.
What's A again? A is the first.
But let's remind ourselves of what A is. A is the first guy. Let's call it. This is A. A is the first set that contains I. Okay. And let's remind ourselves what this W of something are. Well, we said that these guys all had the same weight, W of 1. These guys all had weight W of 1, so on. And these guys all have weight W of, sorry. These guys over here have weight W of A. And that includes I. So the weight of I is exactly W of A. And so this is not even an inequality, it's an equality. Equality. which had better be inequality because this is an extremal point, and so it's going to be on the boundary. Okay, it is an equality. This is true. V is feasible. So we have feasible U and V that satisfy the conditions of weak linear programming duality, and therefore these are optimal points. Okay? So what I just showed is that U is an optimal solution to the linear program. Okay? But Q is the only solution to this linear program, yet I just proved that U is a solution. So Q and U are the same point, and therefore my vertex of Q sub m actually was a vertex of P sub m, as I claimed. It's kind of a long-winded proof, but it's really nice, and everything kind of fits together perfectly. And there it is. That's the proof. Now, so this is the kind of argument that really, it's people that were interested in the greedy algorithm that came up with arguments like this. And if you are used to linear programming, then these are the kinds of slick arguments that they come up with, and they just kind of have this real practical question, and then they encode it into these beautiful systems of linear equations, and then things just fit together, and they prove these great theorems. And if you've ever seen the kind of thing they do, you can tell that this is this is their work. Okay, stop there. See you guys next time.
Yeah. I just did those three things. Your computer. Yeah.
I finished last night. It was 11 ish. I'm not just like that.
So you have a few minutes to talk about it.
Yeah. I had stuff I wanted to add, but
So I was thinking about doing some more reading too. And maybe I read this before and just wasn't thinking about it necessarily, but that finite, if you say every finite subset is independent, then we put that set in there. That axiom, what that does is makes the thing have finite circuits. But there may be infinitely many finite circuits. But each circuit is finite. So that's what, in my thing, that might not be true.
If I get two diagrams, I want to arbitrarily label them, but then swap it.
Do you have office hours today?
Yeah, right now we're
I got students where I think also coming to talk to me. Which is good. I hope. Oh! Karen, have you this? Go! Go! Karen, it was great. It was beautiful.
Thank you.
She goes on Friday, and Debbie goes next week. And I've been holding it off for months.